Let's take a bit of a closer look at time homogeneous processes in the discrete time case. Discrete time will typically mean the non-negative integers as our time index. Now remember, the Chapman-Kolmogorov equations in the context of a time homogeneous Markov process say this, that the transition operators form a semigroup, that Q of n plus m is Q of n composed with Q of m, of course in either order because n plus m is m plus n. So in particular, that means that for any time n, Qn is the same as Q1 composed with Qn minus 1. And then Qn minus 1 is the same as Q1 composed with Qn minus 2, and so on. So what we get is that Qn is actually Q1 composed with itself n times. We have a discrete dynamical system. And so the transitions are ultimately controlled by just this one transition operator, Q1, the one-step transition operator. So let's look at an important example. Once again, random walk. Here our random walk will be in Rd if we like, and the steps can be continuous steps. That is, we'll take an IID sequence of random vectors. They can have any distribution that we want on Rd, and xn is the progressive sum of the first n of those steps. We've established that this is a Markov process, in fact the best kind. It has independent increments, and that means that its transition kernels are given like this. Q of st applied to f is just the expected value of f at the point in question, x plus the increment, xt minus xs. Now in this case, where we only care about the one-step transition kernel, that is, we can take the increment to be x1 minus x0. And for this process, x0 is just 0. So that's just this right here. If we use the change of variables formula, we can write this as the integral of f at x plus y integrated against the law of c1 dy. And there's the description of our transition kernel. For example, if our state space was also discrete, say the integers, and we take the steps to be potentially biased Rademacher distributed, meaning that there's probability p of taking value 1 and probability 1 minus p of taking value minus 1 for some p between 0 and 1, then this says that the transition operator for one step has the action of shifting the function to the right by 1 times p, and shifting the function to the left by 1 times 1 minus p. We could easily iterate this n times and write down a simple formula that has shifts of f between n and minus n with different proportions of p's and 1 minus p here. And you would quickly see that what we build up here is the integral of f against the binomial distribution of parameters n and p. In some sense, that tells the full story on this random walk for this distribution. Of course, we may want to ask much more delicate questions about what is the long-run behavior? How far are we away from the origin at a given time on average? Those kinds of questions can in principle be answered by carefully studying just this one transition operator. Now, following this example where we have both discrete time and discrete state space, let's look at that a little more carefully. So if we have a Markov process in discrete time with discrete state space, and again what that means is that the state space S is countable and the measurable sets are taken to be all subsets, then in that case we have our transition kernels here. Well, because it's a discrete state space, we can calculate the transition kernel on any measurable set in here by adding up over all the elements of that set. And so we have the transition kernel probability mass function involved. And now, if we apply the Chapman-Kolmogorov equations, this is again in general here, not necessarily in the time homogeneous case, we've seen that this just amounts to matrix multiplication, where we sum over all intermediate states, y1 through ym minus 1 in S, and all y in B, of qn plus 1 from x up to y1, qn plus 1 up to n plus 2 from y1 up to y2, and so on down to qm-1 up to m, ym-1 up to the state y. Now in this discrete setting, the probability mass function is just the conditional probability as you established on a homework set. That is, the transition kernel from time n up to time m at states x and y is just the probability that xm at the later time is equal to y, given that xn at the early time was equal to x. Now, if we have a discrete space, discrete time Markov process that is time homogeneous, what that means is that all we ultimately really need to know is the one-step transition kernel probability mass function q1, which is q01 if you like, and that is the probability that x1 is equal to y, given that x0 was equal to x. So let's look at a specific example here called the Ehrenfest-Ern model. This is a very simple model of chemical diffusion in a solution where we have a beaker that contains a semi-permeable membrane, and we have two kinds of particles on either side of the membrane, but we allow them to diffuse across the membrane, and the way that that is modeled is that at each discrete time step, we choose one of the particles in the whole bin uniformly at random. We remove it from that side of the membrane and add a particle on the other side of the membrane. Now let's let xn denote the number of particles on the left side in this picture as time evolves. It's reasonable to model this as a Markov process. After all, at each time step, we're doing some uniformly random thing with no reference to what happened before. So the future shouldn't really depend on the past before the present time. Well, if it's going to be a Markov process, we need to write down its transition kernels. And because it's a discrete time, discrete space Markov process, all we need are the one-step transition kernels, the probability that one step in the future we're at state j, given that at the present we were at state I. Once we have those transition kernels, then we can build up all of them from this formula. Okay, well, for starters, at each time step, we will either remove exactly one particle from the left side, or we will add exactly one particle to the left side. And so unless I and j are exactly one apart, we can't get from I to j in one step. So that means that if I minus j is bigger than 1, or if I is equal to j, this transition probability is just 0. So we only have to care about these two cases, if j is equal to I minus 1 or if j is equal to I plus 1. So if j, which is the state we're supposed to end up in, the number of particles on the left-hand side, is 1 less than I, which is the number of particles we started with before this time step, the probability of that happening, which is the probability that we chose one from the left-hand side and then moved it over to the right, is just going to be, because we're choosing uniformly at random from the n particles in the bin, the number of particles on the left-hand side divided by that number n. And we're conditioning on the case that x at time n, the number of particles on the left at time n, is I. And so this is I over n. Now, what about the other case where j is equal to I plus 1? Well, we can do exactly the same analysis on that side, or we can alternatively say that, hey, for fixed I, we know that this is a probability measure in this set here. And so that means that if we sum up over all of the j's here, we have to get a total of 1. And we know that in all cases, other than j is equal to I plus 1, we either get 0 or I over n, which means that we have to have 1 minus I over n here in order for this to be a probability kernel. So there are our one-step transition kernels, q, n, n plus 1 from I up to j. And now let's just notice that this explicitly has no dependence on n, the time parameter. The n that appears here is the number of particles in total, which doesn't change. So this is the same thing as q01 of ij, or in the time homogeneous framework, we just know this as q1 ij. That is to say, this is a time homogeneous Markov process. Time homogeneous Markov processes in the case where we have discrete space are, in some high-level sense, very easy to handle, because, as we've noted, this is essentially just matrix multiplication. Well, let's actually formalize that, at least in the finite state space case. But first, let's introduce some new terminology. If we have a Markov process with a discrete state space, either finite or countable, it is often referred to as a Markov chain. The idea is that if we, a la Komogorov, model this as a measure on path space, the paths in question here are discrete paths that jump from one state to the next, forming a chain of states. Now, to be clear, it's still called a Markov chain even in continuous time, and we'll deal with some of the subtleties of that in the next lecture. Let me also clarify that some authors will refer to a discrete time continuous state space process as a Markov chain as well, although I won't use that terminology. So the more general random walk that we started with, where the steps could be sampled from a continuous distribution, I will not refer to that as a Markov chain, but some authors might. The only thing that everyone agrees to is that a continuous time non-discrete state space Markov process is not a Markov chain, it's just a Markov process. Those are, of course, the hardest to deal with, and we'll look at that a little bit in the coming lectures. Now, for discrete time and space, in some sense, the entire analysis of Markov chains boils down to questions of linear algebra. Let's see why. If we focus on that case, let's let nu k be the probability mass function of our process at time k. So that is, nu k is the function which takes each state I and produces the number, the probability that xk equals I. Since our state space is discrete, that is sufficient information to reconstruct the entire distribution of the process at each time. For a Markov process that is time homogeneous, which is what we'll be dealing with here, in order to now fully understand the process, well, at least in terms of finite dimensional distributions, but in the discrete setting, that is all the information the process contains, all we need to understand is the one-step transition kernel, which is just the conditional probability that at step 1 we're in state j, given that at step 0 we were in state I. Well, this is a function on s times s, taking values in the unit interval. It's an s by s matrix, which I'll call P. Now, to really call it a matrix, we would probably really want to assume that S is finite here. So if there are n states, which we'll probably just label 1 through n, this is an n by n matrix. And we can then recover the little n step transition mass function from I to j, as we wrote previously, as the sum over all intervening states k1 through kn minus 1 of one-step transition from I to k1 times one-step transition from k1 to k2 times up to one-step transition from kn minus 1 to j. This is again exactly what the Chapman-Kolmogorov equations tell us. But this is nothing other than the ij entry of the nth power of the matrix P. That's what I mean when I keep saying this is just matrix multiplication. And so that means that if we want to tell the distribution of the process at time n, that is, we want to compute its probability mass function, well, by the law of total probability, that's summing over all states I, the probability that at time 0 we're in state I, times the conditional probability, given that we're in state I at time 0, of the event that xn is in state j. But using what we have written right here, that's nothing other than matrix multiplication again, taking the vector of initial states here, written as a row vector, so I'll write it like this, times the matrix P to the n, and taking its jth entry. So that perhaps is the only subtlety here. We're doing linear algebra with multiplication by row vectors on the left instead of column vectors on the right, which is more standard in linear algebra. But of course it amounts to the same thing up to transpose. So that's ultimately what we need to do. In order to understand the state of the process at each time, we just need to take the nth power of this fixed matrix, which is describing the one-step transition kernel, and multiply it by the initial state vector, and that gives us the state vector at time n. Now, I want to make a couple of comments about this. The first is, and this is a key one, this is not the only information that we have. This alone, this property, does not tell us that the process is a Markov process. A Markov process is one that satisfies the Markov property, and so in particular, conditioned on the full past, we get the same information as conditioning on just the recent past. Or alternatively, as we've seen, that gives us nice formulas for computing the full joint distribution given the initial distribution alone and the transition kernel up to this time. Now we can write that more explicitly in an example like here just to see if I want to know the joint distribution of xn and xm for 2 times n less than or equal to m, well, just barehanded in this discrete example, we can see that that's this conditional probability that xm is in state k, given that xn is in state j, times the probability that xn is in state j, just by the definition of conditional probability. The second term here, by what we just wrote right above, is equal to the row vector nu naught times the nth power of the matrix P, jth entry. And then as for this term here, that's nothing other than the jk entry of the m minus n step transition kernel, which is just the m minus nth power of the matrix P. And as you can imagine, we can write out more general formulas for any finite dimensional distribution of x at any finite number of times in any states that we want. And we can simplify things a little bit using the Markov property when we do that to get different formulas that ultimately result in the same thing. Now, I don't want you to get the impression that therefore all of this is trivial. It's anything but. We have to now fully understand these discrete dynamical systems. What is the behavior in the long run, or in the medium-term run, if we have different kinds of subtle questions, of taking the powers of some matrix? That's a difficult question to answer, and although it's more or less fully understood, it took a long time to do. This is not a course in discrete time Markov chains. We're not going to have time to go through that lovely analysis. That's for a different course. We will, of course, look at several important examples and give the general kind of structure of what goes on here over the next few lectures, among some other things. Just to harp on this point a little bit further, let's look at some appropriate diagrammatic representations and some properties of this transition matrix P. So one nice way, at least in the case of finite state, discrete time, homogeneous Markov chains, is to represent the dynamical system in terms of a graph. If we have our collection of states here, say this one has 5 states that I've written here and labeled as I1 through I5, then we put a graph structure, potentially with loops, labeled by probabilities. So here is an example. Now, what does all of this information mean? Well, for example, this arrow here indicates that the one-step transition probability from state I3 to state I1 is equal to 1/5. And so on around this chain. So this is just a shorthand way of writing down the large transition matrix. Let's note some properties that we have in this diagram. Hopefully I didn't make any mistakes. If I choose any one state, like this one, I5, and I look at all of the arrows coming out of it, the numbers coming out of it must add up to 1. Here, for state I4, there's an arrow going up, an arrow going that way, and those are the only arrows coming out, and they indeed add up to 1. Here, for I3, there's a 1/5 here, a 1/5 here, and a 3/5 there. Now, of course, this is just because we have a probability kernel. We must have, for any fixed state, the sum over all states in the state space, Q1 of I3i. That must be 1, because that's just the probability kernel at I3 and the whole state space S. And that's a probability measure, so it must be total mass 1. Conversely, if we have any one-step transition kernel that therefore satisfies this property, in other words, any diagram like this where the arrows coming out of any node all add up to 1, then we can define a unique Markov chain with that transition kernel for its single steps, just by declaring the Chapman-Kolmogorov equations must hold, which is exactly to say that we compute higher step transition probabilities by doing matrix multiplication of that one-step kernel. And, if you like, by the Komogorov extension theorem, we therefore can construct a Markov chain with those transition kernels and any given initial distribution. That's something to point out here. The initial distribution isn't listed. This is the transition kernels, and so this gives us the family of measures indexed by the initial distribution that we have been identifying as our Markov process. Now let me note here that this is inherently in the time homogeneous setting. We could also draw such a diagram in the time inhomogeneous case, but in that case, the arrow labels would change with n. So we would have a diagram like this where these numbers are themselves functions of n, still satisfying this constraint, of course. Another way to think about that constraint without explicit reference to probability kernels is just to note that by definition, an arrow between I and j labeled with a p means nothing other than the probability that xn plus 1 is in state j, given that xn was in state I, is equal to p. And of course, fixing I, the conditional probability given that x0 is in state I, assuming that makes sense and this isn't a zero probability event, is a probability measure, which means that these sum up to 1. And that's just the sum over j of q1 of ij. Now in terms of our matrix interpretation, that's the sum over j of pij. That is, it's the sum of the ith row. And so we have the Markov matrix that is associated to any finite state, discrete time homogeneous process. It is the matrix of the transition kernel, and it is uniquely determined as such an object by the condition that all of the entries are between 0 and 1, and the row sums all add up to 1. Such a matrix is called a stochastic matrix. And, restating what we said just a moment ago, any stochastic matrix is the Markov matrix of a time homogeneous Markov chain by the Komogorov extension theorem. So at a high superficial level, that's the whole story on discrete time, discrete space Markov processes. The devil is in the details, of course, and in trying to answer whatever questions you have about the particular Markov chain from its Markov matrix. For example, with a random walk on the integer lattice, you'd like to know what's the probability that it eventually returns to its starting point? What's the average distance that it is away after n steps? In higher dimensions, you could ask more complicated questions like, what is the volume of the convex hull of the set traced out by the random walk? These kinds of questions, in principle, can be completely answered only knowing what this matrix is, and it's a very simple looking matrix for random walk. But it turns out that answering those questions requires a lot more technology, and we will dibble and dabble in understanding some of those tools in the coming lectures. But before we do, let's now turn to gaining a high-level superficial understanding of the dual situation where we have a discrete state space, but continuous time.